So in this lecture we are going to learn about this Varignon's theorem. What it says is that the algebraic sum of moments of a system of coplanar forces about a moment center is equal to the moment of the resultant about the same moment center. So the algebraic sum of moments of a system of coplanar forces, that is the forces they lie in the same plane, about a moment center, a single point. If we are taking the summation of moments of all the forces about a single point, that moment has to be equal to the moment of their resultants about that same point. So for example, we have, let's say, F1 and F2 are two forces that are coplanar, and they are concurrent as well in this case. So let us say that the resultant is R. Okay, let O be a point where we are going to take the moment. Alright, so O is the moment center here. The way how we take moment is we multiply the magnitude of the force by the perpendicular distance to that point. So the perpendicular distance is from the point to the line of action of that force. So let's say that this is the line of action of the force, and the perpendicular distance from F1 till that point is D1. So the moment due to F1 is F1 into D1, which is anti-clockwise, so it's going to be positive. Then let us say that the moment due to F2 is the perpendicular distance from point O till the line of action of F2 is D2. Let us say that way. So the moment will be F2 into D2. Again, it is anti-clockwise, so it is positive. And let us say that the resultant is the line. This is the line of action of the resultant, and the perpendicular distance from point A to from point O to this resultant is D. Okay, so these are all your perpendicular distances. Let D1, D2 and D be the perpendicular distance from F1, F2 and R respectively to the moment center. So according to Varignon's theorem, what it says is that the summation of moments due to forces about a point will be equal to the moment by resultant about that same point. So F1 into D1 is the moment due to F1, F2 into D2 is the moment due to F2. The summation of their moments about this point, that has to be equal to R into D, the moment due to resultant. So we need to prove this. Let us say that I orient my X and Y axis such that this point O, it is lying on the Y axis. Okay, so join line AO such that this point O is lying on the Y axis, and let us say that this X I take perpendicular to my Y. So I have just taken an axis here, I have oriented an axis here. So draw X axis perpendicular to it. Now what we can say is, let's say that theta be the angle of inclination of R with X axis. So this is the resultant, and let us say that the resultant is inclined at an angle of theta. Okay, so it is inclined at an angle of theta. Therefore what we can say is, if this angle is theta, then if I just extend this D a little bit downwards, we already know that this D is perpendicular to R, so we can say that this is a right angle triangle that is being formed here. So if this angle is theta in a right angle triangle, this has to be 90 minus theta, correct? One more right angle triangle is being formed, OA and this point. So if this angle is 90 minus theta, this angle has to be theta for this triangle, bigger triangle. Alright, I hope you all understanding this. So R into D is basically, this D can be further written as, like in this right angle triangle, you can see this right angle triangle, AO, this D can be written as AO into cos theta. If this is theta, this angle is theta, D can be written as AO cos theta. Okay, because AO will be the hypotenuse in this right angle triangle. So R into D will be equal to R into AO cos theta. Correct? Therefore, I can write it as RD is equal to AO into R cos theta. Okay. Now, what is R cos theta? If this is the theta, this is R, will R cos theta not be the x component of R? Is it not? If there is a force, let's say R, and this is the angle theta, then this component will be the x component of R and this component will be the y component of R. So I can write R into D is equal to AO into RX. Okay. This is one thing that we have got, that R into D is AO into RX. Fine. Next, let us see. Let theta 1 be angle of inclination of F1 with x-axis. So what we can say is that if this is theta 1, then like I can extend this D1 a little bit downwards, and there is this small right angle triangle being formed in which this angle is 90 minus theta, and then this big triangle is the same way as we have done for this resultant R. This angle will be theta. Alright, so this angle will be theta 1. Now what I can say is F1 into D1. This D1 I can write as AO cos theta 1. In this right angle triangle, D1 will be AO cos theta 1. So F1 into D1 will be F1 into AO cos theta 1. Okay. So F1 into D1 is AO F1 cos theta 1, where I can say that for F1 cos theta 1 is, let us say it is x component of F1. Okay, so this F1 cos theta 1 is x component of F1. Let us see for F2. Theta 2 is the angle of inclination for F2. So if I just extend this beyond, so I can say that this angle is 90 minus theta 2, and here I can say that this angle has to be theta 2. Correct? The same trigonometry we are applying again and again, so there is nothing new in this. Therefore this angle is theta 2. So in this right angle triangle, I can say that D2 is AO cos theta 2. Correct? So F2 into D2 is equal to F2 into AO cos theta 2, where I can write as F2 into D2 is AO into F2 cos theta 2. F2 cos theta 2 can be written as F2x. That is the x component of F2 force. Okay. Now we have F1 into D1 value. We have F2 into D2 value. Let us add them up and let us see what we get. So we also have R into D value, which is AO into RX. Right? So let us add these two components up. What we'll get is AO into F1x plus AO into F2x. I can take AO common. So I will get F1x plus F2x. Isn't this summation Fx? That is, we are taking the summation of all horizontal components. And isn't summation Fx the x component of R? Because R is nothing but summation Fx, summation Fy, and this is your R. So the x component of R is nothing but your summation Fx. So we can say that this is Rx, the x component of R, which is equal to R into D. So that's it, we proved. This is your Varignon's theorem. Okay, hence proved. So for this concurrent force system F1, F2, F3, F4, and let us say that this R is their resultant, what we can say is that Varignon's theorem can be applied to multiple number of forces at a time. So even if there are multiple number of forces, we can apply this Varignon's theorem. What we can say is that F1 into D1, let's say that D1 is the perpendicular distance from this O to the line of action of F1. Consequently, D2, D3, D4 are the perpendicular distance from point O to the line of action of F2, F3 and F4 respectively. So we can say F1 into D1 plus F2 into D2 plus F3 into D3 plus F4 into D4 is equal to R into D, where D is the distance, perpendicular distance from point O to the line of action of R. Okay, so this is D. Let us solve a small numerical based on this. Calculate the position of resultant for given coplanar forces using Varignon's theorem and verify that position by taking the moment at least 3 different points. Okay, so verify at least 3 different points. For Varignon's theorem to hold true, we first need to find the resultant, because what it says is that summation of moment due to forces has to be equal to moment due to resultant. So forces we already have, we already know forces. The unknown is resultant. So first we need to find what is the resultant of all of them. And by looking at all these forces, they are in a vertical direction. So we can say that the resultant also has to be in vertical direction, because there is no horizontal force here. Therefore there won't be any horizontal component of the resultant. Therefore it is simply summation Fy, where 7 is acting downwards. So now we'll follow our sign convention, where right is positive, upward force is positive, and anti-clockwise movement is positive. Okay, so 7 is acting downwards, and negative 7, then plus 5, minus 25. And what to do about this moment? So when we are dealing with forces, we should purely deal with forces only, not the moment. Moment is the rotational effect. And when we are dealing with summation Fy or summation Fx, or for that matter if it is a 3-dimensional case, if we are dealing with summation Fz, then we are purely saying that it is translational case, and in this case there has to be no moment. Okay, so moment should never be added into summation Fx or summation Fy, because this is purely a translational cases that we are adding up. So this moment will be neglected, and plus 15. If we find this, we get it as negative 12 newtons, which means that the resultant is acting downwards, okay, in the downward direction. Now what I will do is that I will take the summation of all these forces at point A, and then I'll take the summation of or then I'll take the resultant, or I will equate it to the resultant multiplied by a distance. So I will get the position of the resultant. Okay, because now see, I know the value of the resultant. What is asked is the position of the resultant, that where the resultant is exactly going to lie on this entire beam, right? So summation MA will be, first let us consider this 7 newtons. So 7 multiplied by its perpendicular distance, which is 2 meters. But what is the sign? So this, if I am taking at point A, let me pin this point, let it be the center of the rotation for all these forces. So 7 will rotate in clockwise direction. Therefore it is negative 7 into 2. Then we have this 5 newtons, which is at a perpendicular distance of 3 meters, and it is rotating at anti-clockwise manner about this point A. So we can say that it is positive 5 into 3. Then we have this 25 newtons, which is rotating in clockwise manner, what we can see here. So it is negative 25 multiplied by the perpendicular distance from point A will be 3 plus 1 plus 2, which is 6. So minus 25 into 6. Now, since we are taking moment, summation of moments, here we need to consider this moment. Okay, so this moment will not come in your translational summations or your translational forces, but it has to be included into your moment forces or basically your summation of moments. So it is clockwise, and we know that for a moment we do not need any distance. Moment is independent of the distance where it is acting. We just have to consider the sign of that moment. So whether it is clockwise or whether it is anti-clockwise. Here we can see that it is clockwise, therefore it is going to cause a clockwise rotation only, and therefore it is negative 5, and we have this 15 Newton which will basically rotate like this in anti-clockwise manner. Therefore we can say that it is a positive, but at what distance? 2 plus 1, 3, 6, 7, 8. At 8 meters it is acting, so plus 15 into 8. When you do the summation of all of them, you will get it as negative 34 Newton meters. So minus 34 Newton meter means that it is a clockwise moment here. And since I am showing the direction, I need not show the sign, okay? I showed anti-clockwise. I'm sorry, it is clockwise, right? So it is clockwise. And I also know that my resultant, this is my resultant, which is acting downwards. So for my resultant which is acting downwards, for my resultant to cause a clockwise movement, should it lie on the right side or should it lie on the left side of point A? You should think here that if your resultant is downwards like this, to cause a clockwise movement here, it should definitely lie to the right side. Only then it will cause a clockwise movement, right? So there has to be a little much imagination that you have to do while solving the numericals of engineering mechanics. It's not rocket science, like it's very simple. So by Varignon's theorem, we can say that this moment of 34 Newton meter, that has to be equal to 12 multiplied by this distance from the point A. So let D be the perpendicular distance from point A. Therefore, what we can say is that D should be equal to 34 by 12, which is equal to 2.833 meters from A. So this resultant force is acting at a distance of 2.833 meters from A. So we got this distance when we took the moment at point A, but why not confirm it with taking moment at other 2 points? So this time I'll take moment at point D, okay? So let us take moment at point D, about D. Now this 7 Newton, and I'm taking my moment at this point, alright? At this point D. So I need to know the perpendicular distance from point D to the line of action of 7 Newtons, which is 4 meters, right? And 7 into 4 will be the moment value, but what would be the sign? So this 7 will be acting this way, around this point. So it's an anti-clockwise moment. Therefore, 7 into 4 will be positive. Then we have this 5 Newtons, which is separate, which is at a distance of 3 meters, and it will be acting this way, which is clockwise about point D. Therefore, it is negative. So minus 5 into 3, and we have next we have this 25 Newtons. It's very interesting to understand this. See, 25 is exactly lying on this point D. So what is the perpendicular distance from 25 to D? It's actually 0, right? Or alternatively, we can also say that this point D is lying on the line of action of this 25 Newtons. So this 25 Newton will not contribute to any moment. Therefore, its contribution is 0. Next, we directly have this 5 Newton meters. Therefore, this 5 is basically clockwise. It need not be multiplied by any distance. So we just need to know the sign of this moment, which is clockwise, therefore it is negative -5. And we have this 15 Newton, which is acting at a distance of 2 meters from point D, and it is causing a rotation, or it will rotate like this in anti-clockwise manner. So it is plus 15 into 2. Okay, so when you sum this up, you will get MD as 38 Newton meters. And similarly, now using Varignon's theorem, see now my resultant is not changing, resultant is downwards only, and I got MD as 38 Newton meters, which is a positive value. It means that it's an anti-clockwise moment here of 38 Newton meter. To cause an anti-clockwise moment, my resultant still has to be this side only, like my resultant has to be on the left side, knowing that it is acting downwards. This downward force will only cause an anti-clockwise moment, right? So my resultant is lying to the left side of this point D, and it is acting at a distance of, let's say, this small d. Okay, so this distance d will be 38 by 12, which is equal to 3.1667 meters from D. So it is acting at a distance of 3.667 meters from D, which is actually 2.833 meters from A. So still our resultant is exactly at the same location where we found it using the previous point A. Let us confirm it with one more point, let's say G. So it's actually a good exercise for you also for understanding how we need to take the moment, what should be the sign and all. So let us take moment about point G. It will be 7 into 9, right? 1 plus 3 is 4, 5, 6 and 9. So, and it is positive because it is acting in anti-clockwise manner about point G. This point has to be pinned and it would be the center of rotation. 5 Newton is acting at a distance of I think 458 meters. So it is acting like this in clockwise manner. So it is positive, it's negative, so it's -5 into 8. Then we have this 25 newtons, which is acting at a distance of 5 meters from point G, which will be anti-clockwise in manner. So 25 into 5 positive. Then we have this 5 Newton meters, again a clockwise moment, so it is definitely going to cause a clockwise rotation, therefore it's -5. And we have this last 15 newtons, which will also cause a clockwise moment of 15 into 3, -15 into 3. So if we sum this up, we will get mg as 98 Newton meter, and it is again a clockwise anti-clockwise moment because we found the value to be positive. So I can say that there is the summation of all these forces is summation of all the moment due to all these forces is going to cause a anti-clockwise moment of 98 Newton meter. And we have a resultant which is acting, it should act on the left side only again of this point G. That question you should keep on asking yourself, okay, that if this is a anti-clockwise moment and if my resultant is downward, on which side should it act? If it acts on left side only, then it is going to give you an anti-clockwise rotation, right? So this 12 into D, it should give you an anti-clockwise moment of 98 Newton meters. Therefore, this D comes out to be 98 by 12, which is 8.1667 meters from G. So this distance is 8.1667 meters from G, which again says that this is 2.833 meters from A. If you calculate it, you will get that as 2.833 meters. Alright, so This was a numerical where we proved the Varignon's theorem. And that's it for this lecture. In the next lecture, we'll see some more interesting and important theorems. Till then, take care. Thank you.